Hi everyone. So thanks for the introduction. I'm Lukas Fenaux, and on behalf of Florian Kerschbaum and his students, I'm going to present fast and private inference of deep neural networks by co-designing activation functions. So first, I'm going to introduce a problem, similar problem to the previous presenter. We have a server with a proprietary model and a client with secret data or sensitive data. And the client wants to infer its data on the server's model without having to share said data. And the server doesn't really want to give its model away either. So we decide to try and solve this using multi-party computation, in this case two-party multi-party computation. And there's already a significant amount of work to do this. So we have the current state-of-the-art being GeForce, which optimizes its algorithms for the GPU, and then moves a lot of computation to the offline phase to really ensure a fast online phase. On the other hand, Coin focuses mostly on quantization of models and then creating MPC protocols that are tailored to said quantized models. And then finally, we have Crypt GPU, which is an extension of the Krypton framework to the GPU. So all the solutions work quite well, but they're still fairly slow. And so we thought we could do better. And one of the bottlenecks in particular in MPC is the activation functions, with them taking sometimes up to 93% of the runtime. And that's mainly due to the nonlinear operations that, like a ReLU, for example, requiring conversion between different schemes of secret sharing. And that conversion can take many rounds and add latency, especially in the wide area network setting. So to solve this, we focus on polynomial approximations of activation functions. And looking at previous work, on the MPC side, previous work used multiple rounds to evaluate polynomial functions, which is not great, because again, in the one, it adds a lot of latency. And then on the machine learning side, previous work was not able to train models with polynomial activations deeper than 11 layers, which is a bit annoying if you want to do deep learning. So to solve this, on the MPC side, we developed a single round polynomial evaluation protocol. And then on the ML side, we created this custom training procedure that allows to train models of any depth and width with polynomial activations. So first, why polynomials? As you can see here on this graph on the right, where you have on the x-axis the round trip delay, and then the total inference time on the y-axis, which we're trying to minimize. We have Crypt GPU, which is the previous state-of-the-art, running a ReLU. And here we have Crypt and Poly, and then we have us at the bottom. And the idea is running a polynomial is actually significantly faster than running a ReLU, even with multiple rounds like in Crypt and Poly. So we want to leverage that to speed up inference. And the way we do a single round polynomial evaluation is we do a single round exponentiation. So if you take x, some input to, let's say, the polynomial, you have the server's share and the client's share. And to compute this in the single round, we perform the binomial expansion of this, the power of the sum. And we have all those powers, local powers that can be computed locally in parallel by both the server and the client, and then they can just do a single round dot product to multiply those together, and then afterwards, multiply the other coefficients that are public values to reconstruct the polynomial. There's another work actually called Honey Badger that also does this in a completely different field and different setting, but they offer a different online-offline trade-off, so we also include it in our evaluations. And so from the single round exponentiation, we can do a single round polynomial evaluation by in parallel computing all the powers. Then we dynamically truncate each exponent, and then finally locally compute the dot product with the polynomial coefficients to get the polynomial back. And all of this is a single round. Now that we kind of figured out the MPC aspect, there still remains the polynomial activation in the machine learning training side. So what we notice is that if you just plug in the polynomial approximation without really thinking too much about it, then as you increase polynomial degree, you kind of have this sharp drop in accuracy. And that's a big problem because a higher degree usually means higher accuracy, or at least a higher approximation, a quality of approximation, sorry. And this is mostly due to what's called escaping activation. So on the graph on the right here, you can see the approximation of the ReLU with the degree 4 polynomial between -5 and 5. And you can see that as soon as you get out of that approximation range, it diverges quite quickly because it's a polynomial. And the issue with that is as soon as you have an intermediate value that gets a bit out of range, then you have this cascading effect where they first kind of step a little bit out of range and then more and more and more. And then when you're doing, when you're training, the weights eventually become none because the intermediate value gets so large, the gradients get super large, and then everything blows up. So to solve this, we have a little pipeline where we first quantize the polynomial coefficients, but we don't do it directly. We actually do quantized mixed integer programming to get a better quantized approximation of the ReLU. And then afterwards, we do polynomial-aware regularized model training to get our model. And this regularized training involves basically 3 main components, with the regularization penalty function being the main one. The idea is we take the input to each of the polynomials we have, and then if it's out of range, we penalize it heavily so that it kind of gets back in range, and to give an incentive to the model to behave properly. We also include clipping only during training to prevent any form of cascades from happening, especially for very deep models. When you have a lot of polynomials one after the other, if one kind of gets out of range, then you can have this cascade happening until the model learns to kind of stay in range, especially at the start. And then likewise, we warm up our regularization, especially for deep and or large models to kind of make it work better and make it scale better. So in particular, this is how our regularization penalty function looks. It's fairly straightforward. So we have just a coefficient beta. And then we take our input, we divide it by b, which is usually set to the range, or a bit tighter than the approximation range. And then we take all of this to a high even power, usually 10. And the underlying idea is if x is lesser than b, then the division will output a value between -1 and 1. And when we take that to a high power, it'll go to 0, basically not penalizing the model when it's in range. But then if it's out of range, it's higher than 1 or -1. And then it kind of blows up exponentially in the penalty to really incentivize the model to get back in range. Then a quick note is the clipping doesn't actually affect the penalty. We clip after the penalty to kind of, otherwise it wouldn't really work. And then the warm-up, the idea is we kind of scale A and beta within the few first epochs to kind of allow for smooth initialization. So our results are very straightforward. So here we evaluated first on CFAR with a VGG16. And this is us at the bottom. So ideally, we again want to lower the inference time. We noticed that G-force is actually better than us in the lawn, but we quickly overtake it as you get to higher round-trip delays. And this is quite nice because, again, this has been a problem in the past with the scaling being quite bad. Then we also evaluate on ImageNet with the ResNet 50. And here we can see we're significantly better than all the other previous works. There is a little bit of a drop-off in accuracy. This doesn't always happen. It happens in those 2 cases in particular, where we lose a couple %. However, that's in the plain text. That's from training with the polynomials. However, we noticed that basically going from plain text to encrypted, we lose quite little to almost nothing. And that means that if with better advancements to training with polynomials, we can kind of bridge this gap. So to summarize, we give a state-of-the-art single-round MPC protocol to evaluate polynomials in the WAN. We propose a novel training algorithm that gives accuracy competitive plain text models. And we achieve 3 to 110x speedups in inference times on large models with up to 23 million parameters while maintaining competitive inference accuracy. So you can see the QR codes for our paper and our code. And yeah, thank you for listening.